Okay, so let me continue with integrands with infinite discontinuities. So this basically happens when we have a vertical asymptote. Okay, so an infinite discontinuity. And so we have a limit of integration, or at some point between the limits of integration, where we have an improper integral. So here's an example. Let's say we want to consider the infinite region in the first quadrant that lies under the curve 1 over the square root of x. So here's our curve, right? And we want to evaluate that from 0 to 1. So if I'm evaluating, right, I go from 0 to 1 of 1 over square root of x dx. So right here, this 0 is what makes it improper. So what I'm going to do is I'm going to rewrite it so that we have a portion from a to 1, and we're going to basically approach a from the right of 0. So we're going to rewrite this from a to 1 of 1 over root x dx. So if we're just evaluating this part here, right, well, that's going to be x to the negative 1/2, so that will be x to the 1/2 over 1/2, or 2 root x, evaluated from a to 1. So we'll have 2 root 1 minus 2 root a, or 2 minus 2 root a. And so now, as we take the limit of that, right, the limit as a approaches 0 from the right of 2 minus 2 root a, we get 2. Therefore, the area under the curve from 0 to 1 is equal to 2. Which, again, if you think about it, that's kind of strange, because we're basically saying, right, this is infinitely, but remember, it's getting infinitely closer and closer to the y-axis. So even though it's got an infinite region, as we look at the limit of that, it has a finite area, which is 2. Okay, so let's look at the rules for this specifically. So we have, let's say it's continuous on a half open interval from a to b. Then we need to consider approaching a from the right. What if b is our infinite discontinuity? So we have to approach b from the left. And then what if there's something going on in the middle? We have to break it up into 2 separate integrals. It is kind of like what we looked at in the previous section. So with parts 1 and 2, there's only one integral here. So if the limit is finite, then it converges, and that's the same value. If it fails to exist, it diverges. Part 3, we have 2 integrals here and here. So if either part, right, both parts have to converge, and they have values. Otherwise, if one or both parts diverge, then there's no value. Okay, so state why the integral is improper, and then evaluate the integral, or state that it diverges. Okay, so if we look at this one has a vertical asymptote at x equals 1. So that means it has a discontinuity. So I'm going to rewrite this as, right, if I think about this from 0 to 1 of, I'm just going to write x minus 1 to the negative 2/3 dx, plus the integral from 1 to 3, because 1 is where it's broken up. And now I'm going to write each of these with the limit. So this one's going to be the limit as b approaches 1 from the left, and then the integral from 0 to b of x minus 1 to the negative 2/3 dx, plus the limit as b approaches 1 from the right, and that's going to be b to 3. And again, the b approaching or the a approaching, you can technically use whatever letter you want. Doesn't matter. Okay, so here we go. We got the limit as b approaches 1 from the left, so that'll become x minus 1 to the 1/3 over 1/3, or 3 times x minus 1 to the 1/3. And we want to evaluate that from 0 to b, plus, same thing here, so it's going to be 3 x minus 1 to the 1/3, and this time we want to evaluate from b to 3. And now writing it all out, so we'll have 3 b minus 1 to the 1/3 minus, looks like I gotta plug it in, 3 times 0 minus 1 to the 1/3 plus, oops, let me put my limit in there. Limit as b approaches 1 from the right. I know it's very tedious. There's a lot of writing here, so it's like, but you'll see it'll all come together in the end. Let me plug in my laptop. Okay, so now we just get to evaluate. So there's all those steps in the middle, but then as we evaluate, what do we get? There we go. Okay, so let's see, as b approaches 1 from the left, so that'll be 3 times 0, right? And the next part, that's going to be negative 1 to the 1/3 power. So that's just going to be 1, negative 1, and then you have a negative 3 out in front, so that's going to be plus 3. And then let's look over here, plus 3 minus 1 is going to be 2, 2 to the 1/3. So it's basically 3 with a cube root of 2, minus, and then we look at the last part, it's going to be 0, right? And so our answer is 3 plus 3 cube root of 2. Okay, so therefore, by the way, that converges to that value. Okay, next one, what's the problem? We have a discontinuity, right, again, or vertical asymptote at x equals 2, right, vertical. So I'm gonna, this one's actually shorter than the last one, because if I think about it, right, I want 2 from the left, and we want from 1 to b of 1 over x minus 2 dx. So I have limit as b approaches 2 from the left, that's going to be natural log of x minus 2 evaluated from 1 to b. So we have natural log of b minus 2 minus natural log, and I just realized I should have had this in absolute value, but you'll see in a minute. So that'll be 1 minus 2. Okay, and now as we evaluate, well, as we do this part here, b minus 2, as b approaches 2 from the left, that's approaching what? It's approaching, this part is approaching 0 from the left. Therefore, the natural log, if you recall, what's our natural log look like? So as we go further and further, what's happening here is we get negative infinity. And so this part will just be natural log of 1, which is 0. Therefore, it diverges. Okay. Sometimes we cannot evaluate an improper integral directly, so we first try to determine whether it converges or diverges. If the integral diverges, we're done. But if it converges, we can use what's called the comparison test to see whether it converges or diverges. Okay, so we have to have continuous functions. Okay, and this is going to be for when g of x is greater than or equal to f of x, and it's greater than 0, so everything's above the x-axis. So if we can show that g of x converges, so if the bigger one converges, then we can say the smaller one converges. Okay, and on the other side, we have the converse. So if f of x, which was the smaller one, if the smaller one diverges, then the bigger one diverges. Okay. So we want to use the comparison test to determine whether the integral converges or diverges. So here's how it looks. We take 1 over x cubed plus 1. So I can't use, to integrate that, I can't use integration by parts. You know, it's not x squared plus 1. That would be tangent inverse. We can't use substitution. So we can't really just integrate this by hand. So what we're going to do is we're going to compare it to something that is either bigger or smaller. So I'm going to compare it to one over x cubed. Now 1 over x cubed, so this has to be less than or equal to 1 over x cubed, because adding 1 will make that denominator bigger, which will make the whole thing smaller. So what I'm going to try to do is show that 1 over x cubed converges. Right? So let's take a look. We want from 1 to infinity of x to the negative 3 dx. Okay, so I'm going to rewrite this as b approaches infinity of 1 to b of x to the negative 3 dx. So we get x to the negative 2 over negative 2, or negative 2 over x squared, evaluated from 1 to b. Oh, my 2 goes on the bottom, sorry. So I have 1 over 2b squared minus 1 over 2. Actually, 1 minus negative 2, so that'll be, or minus negative 1/2. So that becomes a plus, and now as b approaches infinity, I get a half, which implies that 1 over x cubed converges. Oops. So since the one that was bigger, right, so the bigger one converges, therefore the smaller one also has to converge. Right, so our integral, I'll just kind of okay, last page. All right, so we're going to compare this one to one over x squared. Right? Again, I can't integrate the 1 over x to the 4th plus 1, but I can look at 1 over x squared, which is going to be bigger than that. So we're going to look at what happens if I look, from negative infinity to infinity of x to the negative 2 dx. Well, we're going to have to break it up into, let's see, I'm going to break this up into a to 1 of x to the negative 2 dx and 1 to b. The reason I'm not going to use 0, so technically we can use any value between negative infinity and infinity, so I just want to pick a real number. The reason I'm not going to use break it up at 0 is because 1 over x squared is not defined at 0. So if I try to evaluate that at the end, I'll end up with something undefined. So that's why I chose 1. Technically, you can use 2, 3, 4, right? We can use anything. Okay, so we have the limit as a approaches negative infinity, and that'll be x to the negative 1 over negative 1, or negative 1 over x, evaluated from a to 1, plus the limit as b approaches infinity of the same thing, negative 1 over x, from 1 to b. So I have limit as a approaches negative infinity, so I have negative 1 minus negative 1, so plus 1 over a, plus, now we have limit as b approaches infinity, I'm going to have negative 1 over b, minus negative 1. Well, as we approach negative infinity, that's going to go to 0. As we approach positive infinity, that's going to go to 0. So I have a negative 1 plus 1 goes to 0. Therefore, so since this one converges, then we know 1 over square root of x to the 4th plus 1 also converges, right? Because we said that one is bigger. Okay, last one, volume of the solid obtained by revolving the curve about the x-axis. Okay, so volume we have, right, it's going to be pi r squared, where r is there. So we have from 0 to infinity of x e to the negative x squared dx. Okay, so this is going to turn into pi 0 to infinity x squared e to the negative 2x dx. So I'm going to do tabular method for this one. So over on the side, I'll get 2x, I'll get 2, I'll get 0. This one will have negative 1/2 e to the negative 2/2, 1/4 e to the negative 2x, and negative 1/8 e to the negative 2x. Right. Plus, minus, plus. Now I'm going to rewrite this as the limit as b approaches infinity from 0 to b of x squared e to the negative 2x dx. Okay, so I have limit as b approaches infinity. And now what did we get here? So we got negative 1/2 x squared e to the negative 2x. Then I have minus 1/2 x e to the negative 2x. And then I have minus 1/4 e to the negative 2x. And we want to evaluate this from 0 to b. And I'm running out of room. Okay, so what I can do here, I can maybe factor out a negative 1/4 e to the negative 2x from that whole thing. So that'll be 2x squared plus 2x. And that'll be plus 1. Right. So what are we going to end up with? So I will have, maybe what I'll do is I'll have 2b squared plus 2b plus 1 over 4e to the 2b minus, and now I'm going to plug in 0. So it'll be, so minus, negative, and then it'll be 1 over 4e to the 0 Okay. Okay, so I have pi. Now this whole thing, right, is all going to go to 0. So I basically end up with pi times a fourth or pi over 4. And that is the end of our very long lesson.